All right, let's take a look at organic chemistry, and we're going to start by taking a look at hydrocarbons. And before we get into the subject matter, let's take a look at some of the chapter objectives. So you should be able to distinguish between organic and inorganic compounds, write condensed, expanded, and skeletal representations for compounds, identify functional groups, use structural formulas to identify compounds that are isomers. So you have to be able to identify isomers. Assign IUPAC names to alkanes. So IUPAC is the International Union of Pure and Applied Chemistry. Draw structural formulas for alkanes when given an IUPAC name. Assign IUPAC names to cycloalkanes. So those are just alkanes that are cyclic. You should be able to write the IUPAC name of an alkene or an alkyne. Chemical equations for reactions of alkenes. So we're going to look at a few different reactions. We'll look at Markovnikov's rule. Chemical equations for polymerization, so polymers. Key physical properties of alkanes, alkenes, and alkynes. Name some aromatic compounds and draw structural formulas for aromatic compounds. All right, so let's start off by talking about what organic chemistry really is, which is the study of carbon and compounds that contain carbon. And just to give you a little background on organic chemistry, it turns out that many years ago, scientists struggled to determine what was responsible for the difference between organic matter that came from living organisms and non-living organisms. So they thought, okay, well, if I have, a flower or an animal or something that's organic, they said, well, where does that come from? Okay, and they thought that there was some kind of vital source that those living beings came from, and they said there's no way a human being could create one of those molecules in a lab that's found in an organic being, again, whether it's a flower or a person or whatever, okay, compared to non-living organisms like minerals, which they said, okay, well, we could make minerals in the lab, and they called this mysterious entity, again, they called it the vital force, and they said that organic molecules couldn't be synthesized, okay, by human beings, okay? And what blew the lid off of all of this was in 1828, Friedrich Wöhler took the inorganic salt ammonium cyanate, okay? So ammonium cyanate is inorganic. It does have carbon in it, but there are a few carbon-containing compounds that are considered to be inorganic. Anyhow, ammonium cyanate, it's ionic, it's inorganic, and when he heated it up, he ended up making urea, which is found in urine, of course. And in his original publication, he said, okay, I took ammonium cyanate, I heated it up, and I made urea, which is organic, and I made it without the aid of dog or man. So he had isolated urea from human urine and from dog urine, but he said I was able to make the urea without the aid of dog or man. And so what an organic compound is a compound that contains the element carbon. In organic chemistry, of course, is just the study of carbon containing compounds. And if you're wondering, well, where would I find a carbon containing compound in my everyday life? Well, you know a few already. Things like carbon dioxide, or maybe you know the formula of glucose, C6H12O6. But it turns out that most drugs, or many drugs, are organic compounds, whether it's, nicotine or aspartame or aspirin, or whether it's morphine or heroin. These are all organic compounds. And so many organic compounds, such as drugs like aspirin, have relatively low melting points compared to inorganic molecules. So if you're interested in healthcare at all, you should know a little bit about organic chemistry. Why? Because drugs are, generally speaking, organic compounds. Okay. And so one of the features of organic compounds is that compared to inorganic compounds like sodium chloride, an ionic compound, has an extremely high melting point. Um, Organic compounds, generally speaking, are going to have much lower melting points. So again, an organic compound is what? It's a compound that contains the element carbon. And organic chemistry is, of course, again, the study of carbon-containing compounds. Now, there's an estimated 500,000 inorganic compounds that have been identified, but more than 9 million organic compounds are known. So there's lots of organic compounds that are known. And if you ever wonder, well, why are there so many organic compounds? Well, it's because of a unique feature of carbon. That carbon can form stable covalent bonds with other carbon atoms. And so something you're going to see is that carbon can form a bond with another carbon atom, and then they can branch off of each other like this. And you might not think it's, oops, I don't know why I put a chlorine there. Anyhow, you might not think it's the most interesting thing ever, but this is actually pretty unique that carbon can form stable covalent bonds, what? With other carbon atoms. And that's why we spend so much time studying organic chemistry because it's such a unique element. Now, table 8.1 just briefly covers some properties of typical organic. So we've got organic compounds and inorganic compounds. Now, this is generally speaking, but if we just go through them quickly, first one is the bonding within molecules. Well, first of all, we don't have ionic, or sorry, yeah, we don't have ionic molecules, but with inorganic compounds, they're oftentimes going to be ionic compounds, whereas when we're talking about organic compounds, they're going to be covalent compounds, okay? The intermolecular forces between the molecules with organic molecules is generally going to be weak. Things like hydrogen bonding, dipole-dipole forces, London forces. Whereas with inorganic compounds, it's going to be quite strong, right? And that's because ionic bonds are much stronger than covalent bonds. Normal physical state, when you're talking about organic compounds, they're usually gases or liquids or solids that have low melting points, whereas inorganic compounds are usually have very high melting points. Okay, if you think about something like table salt, it melts at a very high temperature. When it comes to flammability, well, gasoline is an organic compound, and that has a very high flammability. Whereas if you have something like calcium, I don't know, calcium bromide, which is an inorganic compound, it's pretty much non-flammable. Solubility in water, and again, this is generally speaking. Organic compounds, a lot of them have low solubilities in water, whereas inorganic compounds oftentimes can be dissolved in water. Conductivity, organic compounds, generally speaking, are going to be non-conductive, whereas organic compounds are going to be conductive. And then finally, rate of chemical reactions for organic compounds, a lot of times slow, but with inorganic compounds, faster. All right, let's take a look at our first example. I'll classify each of the following compounds as organic or inorganic. Well, the first compound, this is sodium chloride. Sodium chloride, which is an ionic compound. It's made of a sodium cation and a chloride anion. So it is ionic, and therefore it is inorganic. Doesn't even have carbon in it anyway. All right, and then the next compound, C6H6. Well, this is what we call a hydrocarbon. So hydrocarbon. And a hydrocarbon is some kind of molecule that's made out of carbon and hydrogen. So it's going to have a generic formula CXHY, okay? That's a hydrocarbon. So, and you can see it has carbon in it, obviously, and carbon is in the name. So this is definitely, we'll put here, therefore, organic. If you're curious about this compound, C6H6 is, there's a couple different compounds it could be, I suppose. But anyhow, generally speaking, this is going to be benzene. So if you want to take the time to look up the structure of benzene, it's C6H6. And there's some interesting history when it comes to the discovery of the structure of benzene, which has 6 carbons in a ring all bound together like this, and then you have single bonds and double bonds alternating, and each one of the carbons has one hydrogen bound to it like this. All right, let's move on to section 8.2, representations of organic molecules. And we'll start with structural representations. First, we're going to look at the expanded structural representation. And this is a structural formula showing all covalent bonds. So again, expanded structural representation is going to be showing all of the covalent bonds. Sometimes in organic chemistry, we call this a Lewis structure, like the Lewis structures that we looked at before. Lewis structure, okay, shows every single bond, a Lewis structure. The next one is a condensed structural representation. So condensed structural representation is going to be a structural molecular formula showing the general arrangement of atoms, but without all the covalent bonds. So if we take a look down here, okay, we see the expanded form here where every single bond is drawn in, right? We have every bond between the carbons, and then we have all the bonds between the carbons and the hydrogens in our hydrocarbon. Then in the condensed structural representation, you can see that we have the general arrangement of the atoms, but we're not showing the covalent bonds, right? You can see that we have this first CH3 group here, but we've condensed it down to this CH3. Then we have a carbon with two hydrogens attached, which we've condensed down to this CH2 here. And then finally, we have another CH3 group here, which we've condensed down like this. And in a a skeletal structural representation, this is a molecular formula showing carbon atoms as points with hydrogens bonded to the carbon atoms as being assumed. Other atoms like nitrogen, hydrogen, chlorine, bromine, fluorine, iodine, sulfur, those would be shown explicitly, as well as the hydrogens that are bound to these non-carbon atoms. So if we take a look at our skeletal structure here, remember it says that you have a carbon at every point or the end of a line. So since we have three carbons in our molecule, right, I'm just going to redraw this structure, but here's the rationale. When your pencil touches the paper, that dot that I just made, that's this carbon. Then we're going to make an angle. This is the next carbon, this dot here, and then down here. So we have carbon, carbon, carbon. Now, since carbon always has four bonds, okay, how do we complete this structure, right? If we have the three carbons, and I'll just work off this diagram here, one, two, three carbons, it's implied that there are three hydrogens here. It's implied that there are two hydrogens here, and it's implied that there are three here in order for each carbon to have um, four bonds. And so skeletal structures are really the industry standard. And so you have to spend a lot of time working on skeletal structures. Sometimes we call skeletal structures bond line structures. If you're perusing the internet and you hear somebody talking about bond line structures, they're talking about a skeletal representation or a skeletal structure. Now, like I was saying, skeletal structures that have non-carbons like nitrogen, oxygen, chlorine, fluorine, bromine, iodine, or sulfur or phosphorus, whatever, we put those elements in explicitly, and we also explicitly show the hydrogens that are bound to those elements. So if you take a look at this molecule here, right, we have our CH3 right here. Then we have a CH2 here, and then we have NH2 here. So you can see we've condensed that down to the CH3, and we've condensed the CH2. Oops, let me get my red pen just to be consistent here. We condense the CH2 down, then we condense the NH2 down. But when we're drawing the skeletal structure, we condense the two carbons, the CH3 and the CH2, but we draw the nitrogen in explicitly and we show both hydrogens that are attached to that nitrogen. Okay, this is a rule. And so again, you want to practice drawing your skeletal structures because they are, so to speak, the industry standard. This is generally speaking how an organic chemist is going to draw an organic molecule. All right, recognizing and writing structural formulas is an important skill in biological areas of study because structure determines chemical and physical properties. This is very important. That why are we so interested in structures as chemists? And it's because structure determines chemical and physical properties. Write a condensed structure and a skeletal structure for the compound that's shown here, which is 2-methylpentane. And so let's take a look. So first we're going to do the condensed. So I'll do the condensed with my black pen. So first we have a CH3. So I'll write that down, CH3, like this. But we notice that C2 has two CH3s attached to it, right? There's one here and there's one here. So what I'm going to do is I'm going to put those two CH3s in brackets, and I'll put a subscript 2. That represents both of those CH3s attached to the carbon number 2. So maybe I'll put that carbon number 2. I'll circle it with blue, and I'll write it in blue like this, okay? Then after that, we have two CH2s. So I'm going to put here CH2. I'll put it in brackets. I'll put a subscript 2, which again represents the two CH2 groups. And then finally, I'll put my CH3. So hopefully you can see my green pen, which looks something like that. Okay, so there's my condensed form. So that's my condensed form. Now, if I want to draw a skeletal formula, I'm just going to erase some of my work here. Here's how I would do it. I'd find the longest chain of carbons. So you see how there's 5 carbons in a row here? 1, 2, 3, 4, 5. The way I'm going to do it is that when my pen touches the screen like this, that's carbon number 1. I'm going to go 1, 2, oops, 1, 2, 3, 4, 5, like this. So now I've covered all 5 of these carbons, and you can see on carbon number 2, I've got another CH3, and so there's my skeletal structure. Now, a question students will ask me sometimes is they'll say, "Oh, Mr. Dion, well, you went up on your first bond. Do you have to go up?" And the answer is no. You could do this. You could say 1, 2, 3, 4, 5. It's still the same molecule if I put a CH3 group like this. Okay, so again, the only way you can master this is to practice it a lot. Okay, and don't be discouraged. Everybody has to practice it a lot.